everybody.
Okay, recording. So it's a great pleasure to have Benedikt in Bologna. I always tried to invite him, but he's always traveling around the world. But this time he was here for the ALMA meeting, and I asked him if he could stay a little bit longer when we met in Santa Barbara this May. And then we managed also to organize this visit at the institute, in our institutes. So Benedikt is a, very well-known world-leading scientist on numerical simulation, nonlinear properties of dark matter halo, galaxy formation. He has done many work in the last year since his PhD. So he's one of the first person that introduced in the literature, scientific literature, the definition and the characterization of the splashback rings with his famous work with Andy Kratsov. That was his supervisor in the University of Chicago. So Benedikt did his PhD in Chicago, then he moved to CFA in Cambridge. First as a postdoc, then he was awarded by an Einstein Fellowship. Then he was in Cambridge for one more year and a half. Then he moved to Maryland with his Einstein Fellowship. And now he's assistant professor at the University of Maryland. With his group, is leading many great projects on numerical simulation. He's very interested on the science that we do in our institute, from radio emission. So he was visiting and talking to Franco yesterday. He's interested in galaxy cluster properties. He's interested in small-scale physics in numerical simulation and guided by recent observations. So Benedikt is talking about galaxy cluster as dark matter laboratories, and I'll give him the stage.
Thanks, Carlo. That is a way too kind an introduction. And thanks for hosting me in Bologna. It's been truly a pleasure. It's funny you say I've been traveling around. Like, I feel like I haven't traveled at all. I've just been teaching. But 10 days in Bologna, I have to say, was just the break I needed. So yeah, why take this away? Ooh, how to get rid of this? That's not right. I might have to close this. Okay. Yeah, so why clusters or dark matter halos at all? Right? I mean, it's sort of like, I feel like you were describing my PhD, right? It was all very theoretical, simulation-based. And I guess the one thing I've learned in astronomy is that we only care about things that we can eventually observe. And so this is sort of where this talk is going, right? Like, can we actually observe dark matter halos, even though we can't see them? And then what can we learn from those observations about really fundamental physics? So what's the fundamental physics? I mean, when you look at a simulation of dark matter collapsing, which I'm showing here in not in co-moving coordinates, so you see the Hubble flow actually ripping the universe apart and gravity eventually winning on small scales and making the cosmic web. There's really sort of three things you can ask about this, namely, what's the particle nature of the dark matter? What is the nature of the gravity, right? Is it modified? Is it general relativity? And what's the cosmology that seeded the initial field, right? And once you've defined these three things, then you know everything. And so the idea is that hopefully in the galaxy clusters that sort of live in the biggest halos, you would have imprints of ideally all three of these things. Right? So that's where all of this is going. So the idea is, if you could measure the structure of these clusters, you might learn a lot, right? Now, by structure, I'm going to mean essentially the spherically averaged density profile. So you go out in radius, you make some plot that's like log R versus log density. And these things have been studied to death, ever since, I don't know, the 80s. And nobody agrees on anything except that they steepen, right? So you have a shallower profile at the center, and then this gets steeper and steeper. And there's this radius where a slope is -2. So what d log rho over d log r is -2. We call that the scale radius. That's fairly far in. So you want some other definition of the outer radius. And for that, people typically use something like the virial radius or something where you just define an overdensity, right? You ask, what's the enclosed overdensity? And you go out until you hit, I don't know, 200 times the mean, something like that. Now, is there a simple way to understand this? I would say there sort of is, actually. right? So often this halo theory sounds complicated, but it's really simple in many ways. So here's how it goes. So you're starting from the cosmology, right? This Gaussian random field. Now, if I ask you what the peaks in the Gaussian random field look like, one would be very tempted to say Gaussian, right? That's wrong. So they don't look Gaussian. They're also not a top hat. There's sort of something in between. So they're kind of shallow at the center and then steep at the outside. That just sort of comes out of math. So why does this matter? Well, because when you're collapsing something that's very flat, it's almost like a top hat perturbation, right? Just the sphere of matter collapses more or less in one free fall time very quickly. And so you get, if you plot time and then mass of the halo that you're making, this is a very fast growth. And then you get to this steeper regime and it slows down. It's a bit like humans, you know, there's sort of a time in your life when you kind of start to slow down and then you, I don't know, you do less and less. And so we can define some sort of formation time where you know, some characteristic scale where this happens. Now, again, why does this matter? Well, because in turn, this history imprints itself on the density profile. And that's because you can think of halo formation as just shells piling onto a halo. And the shells know something about the mean density of the universe at the time when they were accreted. And so if you're doing this very quickly, the mean density is more or less constant. And so all the shells have the same density. And so you're making a shallow profile. And then once you get to the slow accretion regime, the density of the universe goes down a lot. And so you're making a steep outer profile. So basically, you can think of this scale radius, this where the radius where the slope is -2, as being related to the formation time, right? So sort of locked in at that time when the halo goes from fast to slow, more or less. Now, if all of this was too complicated, you can think of it just as simply halos are basically contraction of these initial peaks, fundamentally. Now, people want to, of course, make fitting functions to express all of this. There's something called the Einasto profile. So this is just a function where your slope continuously steepens, looks exactly like this comic. But then more frequently, people use the Navarro-Frank-White profile, where you're positing that you have two slopes on the inside and outside, and they're -1 and -3. And people have made a big deal about these numbers, and we'll see why. I think they're not really all that significant. But immediately you see a big difference, right? So in this profile, you have a slope of -1. The Einasto profile had a slope of 0, as in flat at the center. So those are two totally different things, right? That we can old plot, but you know, there are many plots like this where people try to distinguish. In this case, via dwarf galaxies, you're somehow measuring rotation curves and so on. And it's incredibly difficult, right? Immediately you see you can't really distinguish these two totally different scenarios. And so this is just really hard. So we still don't observationally easily know what this density profile really is. Now, here people are trying to say very small radii, right, like 100 parsecs, so these very centers of dwarf galaxies. And that's great. But you're also very affected by the galaxies, by the baryons there, right? So you're not just understanding dark matter. And so today I'm going to argue, not that we shouldn't do that, but that we should also go to much larger radii, sort of beyond this very radius or something, because there's also really interesting stuff to be observed out there. By the way, feel free to interrupt if something is unclear, right? Completely informal. So what would we expect out there? Well, again, if you think of halo formation as this kind of shell picture, you can write down these models. This was all done in the 80s, where basically you assume that there's sort of a point perturbation, right? You make an infinitesimal denser point, and then you imagine that the universe is full of just dark matter, no dark energy, and it's in shells around this perturbation, right? And then everything sort of outside of this turnaround radius is expanding, and everything inside the turnaround radius is collapsing into this perturbation, and the turnaround radius grows as you get more and more gravity. So the shells fall in, it's collisionless, so they go right through and they start orbiting back and forth in the halo. And you immediately notice by eye that there is this characteristic scale here, right? So this is where the shells come in, they come out the other side, they get very slow, they hang out for a bit, and then they fall back and orbit again. And this is what we call the splashback radius. Some people have called it the second turnaround radius, whatever you want to call it. There's sort of this prediction that there should be this characteristic scale. And another way to think about it is that the scale separates matter that's sort of falling in for the first time, right? It's never been in the halo, from the stuff that's orbiting back in. And by the way, this would also go for satellite galaxies, right? So this matters in clusters. Like, have you orbited? You're probably red and dead, right? Have you not? You might have fresh star formation. To give you a sense for those who study the local universe, right? If you look at the local group, if you imagine Milky Way and Andromeda halos, often people use virial radii, then they're sort of apart, moving towards each other, but separate. But if you look at the splashback radii, they're actually already overlapping, right? So our halos are already touching in reality, and we could even exchange satellites dynamically, right? The orbits could be within each other. So, so far with the theory, right? So now the question is, how can we observe any of this? And this is where I think going to galaxy clusters is a really good idea, right? Because in principle, everything I'm telling you about is true for tiny halos, right? I mean, literally Earth-sized halos will follow the same relations as a big cluster halo. But observing the latter is much, much easier because we get these sort of observational tracers that we just don't get everywhere else. Namely, we get the distribution of the galaxies that make up the galaxy cluster. We get weak lensing, as in the bending of light due to all the total matter. We get the stellar halo of the brightest cluster galaxy, right? So these brightest cluster galaxies are kind of extended, as we'll see a bit later. You get the SZ effect, as in the scattering of CMB photons from hot electrons, and you get X-rays, again, from hot gas at the center, right? So these are all things, well, I mean, you get satellites as well around smaller halos, but you might have like 2 instead of 200. By the way, down here is one of these stellar halos, right? So this is M87, the center of the Virgo cluster. Spectacular. Okay, so what is the status of these observations? I mean, there are many, many things that have been done with this. I'm going to focus on what is our knowledge of the dark matter or the total density profile at these large radii. And there's been a real explosion of knowledge in this field. I've put some of the faces that were leading this explosion over the last 10 years or so. So here are results from the dark energy survey. It's a busy plot. So let's walk through it. So up here you have the density profile. So it's a function of radius density, and red is weak lensing and blue is galaxies. So the first thing is they agree, which is crazy, but we can get there later. Probably a coincidence, if you ask me. The signal to noise is crazy, right? I mean, you're measuring the dark matter density profile here, something you cannot see. Right? So this is, to me, it's revolutionary. The features might be a little hard to see, so it's often good to look at the slope. So d log rho over d log r. For orientation, this green line is an NFW profile, right? So that's where the slope goes from -1 to -3 in this sort of S shape. And indeed, I mean, the profile does steepen, right? So we see the slope going down, but then there is this sort of dip here, and then comes back. And that's because that's where the splashback radius is, right? So you have your orbiting stuff that sort of starts to drop off a bit more steeply here, and then you hit this infalling stuff that's coming into the cluster for the first time. The simulations are black lines, amazing. They seem to agree as well. Seems like we're done here, right?
It's a coincidence.
The simulation? Probably. I mean, no, that's not. I mean, some people predicted this, right, from simulations, that there is this feature, and it was very exciting when it was first found. This is a little more. I think this was illustrious TNG even compared to even hydro simulations. But so the satellites, this is crazy that it agrees because that's not so clear, right? That it should really match the total profile. Anyway, it's a story for later. So how come we're not done, right? So why am I standing here telling you about this? Well, I think there are many things we don't understand. So namely, what really is the relation between these tracers? Why does this very simple interpretation of satellite galaxies work? But also in theory, there's some questions. So what I'm going to do is I'm going to talk about theory first and then observations again. Right? So let's start with the theory. So this thing that they're plotting here is actually an extrapolation of what they're calling the halo, right? So the orbiting term. And this was from our fitting function from 2014. Unfortunately, I don't believe that anymore because this was really just a function that was sort of we made, but it's not really meant to be extrapolated. So what's the issue here? So when you think about this orbiting infalling paradigm of these profiles, then you have something like this, right? So you have your orbiting density profile that sort of goes down, and your infalling profile that does something. Down here is the slope again, by the way. The problem is you don't know what this is, right? Because you can't really see it, and it's completely swamped by the orbiting thing, and vice versa. You cannot see this orbiting term at large radii because it's totally swamped by all this infalling matter. And so I would argue that previously we did not know what these density profiles really are physically, right? So you have these formulae like NFW, INASTO, but they're just guesses, right? Because they're not trained on this, and neither was our formula. It's not a critique, it's just the fact that we didn't have this information. But in simulations, I mean, you do have the information, right? I mean, you could in principle, I mean, you look at a halo forming, you see all this matter falling in smoothly or in subhalos, and then you see it starts orbiting, right? And so why not, you know, pull it apart and decide what's infalling, what's orbiting, and figure it out. And it's indeed what I did. It's just quite tedious because you have to do it for each particle individually now. So in this video, each point is a virtual particle in a simulation. You see one halo forming. And initially, I'm making the particles purple, which means infalling, as in they have not orbited yet. And then we apply a very simple criterion. If a particle has undergone one pericenter, right? If it's gone past the center, then we're going to call it orbiting, make it orange, and count it into this orange density profile. So down here, you have the live density profiles of these two components, rescaled by this white circle in radius, and then the mean density of the universe. I'll show you one more. What you can notice is that they're actually pretty constant, right? So this starts at, I don't know, z equals 4 or whatever, but they don't really change all that much. The infalling profile looks like sort of a power law, and the orbiting one, indeed, it sort of seems to steepen, and then it really cuts out, right? So there's a radius where you really have no more orange particles. And this turns out to just be energetics, right? So there's really a radius where you can't get energetically. But an NFW profile would go like, you know, extends to infinity, basically. So now we can do this for billions of particles in a bunch of simulations, right? It's, again, supercomputing tedious and so on, but it can be done. And then you have all these infalling, orbiting, separated halos. So let's look at some density profiles. I'm going to throw a bunch of lines at you right now. So again, stop me if it's too fast, and I hope it's not too technical. So let's just look at two samples to keep it simple. So this is the total density profile, again, sort of this thing, orbiting, infalling, and the slope for two samples, one where the halos are growing fast and one where they're growing slowly. And you might be like, whoa, whoa, like, why that separation? Why not mass or something? So it's actually easy to understand. Imagine you're a particle, you're falling into a halo, and then nothing happens. Well, what happens is you go on an orbit, and you're just going to sit there forever, basically. However, if the halo is now accreting a ton of matter, then your orbit's going to keep contracting until no more matter is being added, right? So you can think of mass accretion as just contracting the density profile. So indeed, what we basically see is that this orange sample, this is the one with these quickly growing halos. It has this very prominent splashback thing with its prominent edge. And then in this one, you can even see the second orbit of particles, which is pretty cool. But now we can do the cool thing and separate this into orbiting and infalling. Right? So this is just the orbiting, the median orbiting profiles of halos in the sample. And well, first, we actually see that this scale goes down to 10 to the -2 mean densities, right? So you're tracking this at a density way below mean. Totally impossible to see if you don't separate out the components. And indeed, we see this crazy steep truncation, right? This thing really just cuts out. It's very much like a king profile for those who study globular clusters. And then we can also look at infalling profiles, and they were also very surprising. I mean, again, shapes that I don't think were known. They go to a constant for some reason. This is totally not obvious to me still. And they also depend on accretion rate. So there's sort of lots to learn here, right? So I feel like if I had asked you, like, what do halos depend on? The answer typically is sort of mass and redshift. And I'm actually claiming that's exactly not what they depend on, right? They depend on accretion rate, so the dynamical state, this contraction. They depend on halo age, that sets where your scale radius was, right? So there are two different scales in these profiles. And it turns out they depend on cosmology. I didn't show you this, it gets a bit nerdy. And they really don't depend much on mass and redshift at all. So this is sort of always like, whenever I see these plots as a function of mass and redshift, I'm always like slightly itching. You know? This is actually not the best way to plot it. And I've done it myself, of course. Okay, any questions at this point?
the mass define the equation rate and halo age at the same time?
Yeah, so they're all correlated. That's right. So bigger halos are accreting more today, right? So clusters are still growing today on average. Milky Ways are not growing anymore. But you can pull these apart so you can at fixed mass plot different accretion rates. And then you see that really is accretion rate that makes the difference and not mass. But it is true if you just naively plot mass over all accretion rates, then you do get a mass trend.
I think people are using mass and redshift because that is the
Yeah.
you can observe this one.
100%.
And then you look at the correlation because accretion rate, halo rate somehow you can infer, but are not straightforward.
Yeah. I mean, yeah, in simulations, you can of course measure all of this, but even then it might not be in your halo catalog.
Yes.
Also, I mean, redshift is funny, right? Because when you think about it, this has to be true. Halos don't have a clock. Right? I mean, dark matter halo doesn't know it's equals 4 or equals 2, right? There's nothing in the physics that would tell it. It might know about things like the surrounding environment and blah, 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 right? But it's, I don't know, it just cannot depend on time explicitly. Anyway, so, I wanted to make a new fitting function to sort of capture these shapes. So here I'm again showing you these are profiles for a particular, let's call it a mass bin, basically. I've multiplied them by r squared, so it looks a bit different. Compress the range, and then down here is just the orbiting component. So if you use an NFW profile plus sort of a power law for this infalling stuff, this is what you get. And so it just, I mean, it's not designed to capture this, right? I mean, it has the slope of -3. Here the formulae for those who are familiar. Inasto does a little better, it can steepen a bit more, but it's still actually doesn't capture this. Here's a formula that we made in 2014, the one I don't believe anymore. Now you see why, right? Because it's actually also a power law, and it's sort of also, even though it fits reasonably, it's not right. And so here's what I'm suggesting now, which is actually simpler. It's just sort of an Inasto profile. So there's this round, and then there's a second similar term that just cuts it off exponentially. And this is just a fitting function. There's no physics here, But you get the second scale, this truncation radius, basically. And so this works very nicely. You can even apply this to individual profiles. When you fix alpha and beta to these numbers, then you have a 3-parameter fit. So that's the same as an Inasto profile. And you can statistically show that it fits a little bit better than Inasto, which tells you that even in these noisy individual profiles, there is this preference for that sharp cutout, basically.
So these alpha and beta are meant to be like universal?
Yeah, that's a good question. I'm working on this they're sort of almost universal. So I'm claiming alpha is more or less universal, and this is contradicting some previous work, and we can talk about why. Beta is sort of funny. It's not quite universal, but it also doesn't have a well-defined relation. But for individual profiles, this beta equals 3 works pretty well.
So from an analytical point of view, how do you model this inflow? So I understand the orbiting.
Yeah.
It's not much more familiar, but this inflowing.
So I modeled this very badly as just a power law. And it turns out that there is a problem with this. So it's okay. I mean, you can fit it well, as you can see here, out to sort of 10 or 200 M. But it's not really a power law, and you shouldn't think about it like this. It is sort of just this nonlinear infalling term. And I'll tell you in a second where actually was like one of my next slides, in fact. Yes. Let me say this real quick and I'll tell you. So we have this collaboration, this sort of physical halos or dynamical halos collaboration. So Eduardo Rosso in Arizona, some of my students and his students, and we're working on exactly this, right? Like understanding the infalling profile better from first principles. Right? So Zeldovich collapse and so on. Building a halo model, based on all of these insights and so on. So it's sort of a large scale structure component. So we're asking many questions like, can we find a simpler algorithm to make these distinctions? So for example, people often ask me, can't you just do this in phase space, right? So phase space is when you just plot the radial velocity versus radius and you get something, for the total halo, you get something like this, right? But then you separate it, so this is your infalling stream with negative velocities, right? That stuff's falling in, and then stuff goes on these kinds of orbits, right? So this manifests in phase space. And so you would say in this halo, absolutely not, right? I mean, there's no clear line you can draw. But it turns out you can give machine learning a little more information than this, and actually does pretty well. So this is what one of my undergrads is working on right now. So these are the kinds of questions that we're considering. I wish I could tell you more, but we don't really have time. So the point is, like the infalling profile, there is a lot to be done to understand this. There's no model at the moment that's really good and physical. But ask me again in a year.
Can you derive this from linear theory? You can use the bias, the linear prospection.
Yeah. The problem is that a lot of these models, so what Carlo is talking about for the non-specialists, right? You can do these things where you take the correlation function of matter, you multiply it by some halo bias, and then you get some sort of profile thing. So it turns out this is actually all not that accurate in this region where you do get nonlinear infer, right? Because the stuff is already really accelerating towards the halo, so it's getting boosted, right? It's above what you would get just from linear theory, and it turns out to be quite nasty. This is not easy to build a model for this stuff. So yeah, we'll see how far we get. So I want to come back to observations though, because just to remember the sort of motivation for all this, right? So we started from fundamental physics. So here are just a few more simulation plots from other people that have done this with sort of self-interacting dark matter. So when particles collide, and you see that the slope of the density profile can slightly change. Same with modified gravity. People have shown you can get effects of this, right? And these are small effects. But we also have like Euclid and LSST, right? I mean, we can be ambitious. We're going to measure these things to really high accuracy. And so the question is, what do we get from all this? And so I want to come back to this picture. So the idea is, and I'm working on this with Alexi Leoto from UC Santa Cruz, Song Huang, some of my students. Again, it's a bigger collaboration. What we're thinking about, what will it take to really measure this? And the idea, again, is to use as many of these tracers as possible, except for X-rays. Not because we don't like X-rays, but because none of us have access to X-ray service. Anyway, also there's questions. I think X-rays are kind of hard. So the question is, why are we doing this now? Why hasn't this been done before? And the answer is because now we have sort of overlapping surveys, right? So in the past, if you looked at sort of, SC like CAB surveys, right? And then you need a really high resolution galaxy survey. Then you need something like Euclid for weak lensing, right? And then you need them all to overlap at the same clusters, So now with these bigger footprints, this is beginning to happen. So what's the idea? Basically, we take dark matter only simulations, hopefully of many different cosmologies. And they give us the things that we want to measure. So mass, accretion rate, density profile. And again, the whole density profile is important because we saw the signatures of physics can be at any radius, right? So we want to ideally constrain the whole halo. And then we build a fat forward model, right? So on top of the simulation, we have recipes for weak lensing you more or less measure, but then, satellite galaxies you have to put in, stellar halos, and you have the low-rich gas and so on, right? And then you use some fancy machine learning-y sounding word like emulator or something, right? Some numerical quick, fast connection between the two. I really don't like calling this machine learning. I think it's like overboard, but anyway. And you have nuisance parameters, right? So you have your baryonic effects and so on in there. You want to marginalize over all of this. Throw it at real clusters and see if there are any constraints on these quantities. Right? So it's not easy because the data is noisy and so on. But that's the fundamental idea. So now you might say, why do you start from a dark matter only simulation? Why not something like illustrious TNG, where you just have all these things? The problem is, you only have one cosmology, right? Typically, because they're expensive. And more importantly, you only have one baryonic feedback model, right? You one model for galaxy formation. And you just don't know if that's true, right? So how can you use that for inference? You cannot. You have to marginalize over the sort of possibility space of all possible galaxy formation models, which is crazy, but can be done, I think. So anyway, we're working on all four of these components. I want to show you some work that one of my students has been doing on these stellar halos, because I think this is a really new idea, right? So these stellar halos have come into focus. I mean, if you look at SDSS and you look at some of these BCGs, you're like, what's stellar halo? It's just a normal galaxy. But then you look at them in HSC and you just see these crazy envelopes. They go out hundreds of kiloparsecs. It's really beautiful. And so Song Huang was studying these and he found something nuts. So he was measuring the halo mass with weak lensing, which they also have really high quality data for. And he found that if you measure the mass in a ring between 50 and 100 kiloparsec, that is more tightly correlated to the halo mass than the total stellar mass of the galaxy. Think about that, right? So the ring out here tells you more about the halo mass than the total stellar mass. That sounds crazy at first, right? But it actually makes sense because so now we can use these hydro simulations at least to give us some physical insight. So here is illustrious TNG50, these beautiful gas motions at high redshift. But not high anymore at this point in the video. Anyway, so we're transitioning to the stellar halo that's forming here from these two merging systems. And so we see that stellar halos are really built up of these shredded satellites. Right? So if you measure only the light in the stellar halo, you're measuring the merger history, these halos basically. Right? And that turns out to be very tightly correlated with the total dark matter mass, more so than the total stellar mass, which depends on galaxy formation. So that's the theoretical background. And so my student Kardialeidik has been applying the observational pipelines to this, sort of to measure things like the observers do. It's been quite fun, and actually the agreement is pretty good. I'm a factor of 2, between these observations in black, which by the way are wrong out here because of background. But this is like going over 4 orders of magnitude in stellar density, right? So it's pretty good actually. And so Katja has been asking like, how are now we can ask any crazy tracer like the stellar mass between 30 and 350 kiloparsecs. How is that correlated to the halo mass, right? And so they made this absolutely monster plot where you have the inner radius here, right? So you're starting, say, at 0, and then you go out to some radius. So this top row is the conventional definitions, where you just take everything out to some radius. And then the color map tells you to scatter with halo mass. So white is good, dark green is bad. And so this top row is not that great, right? So these are the conventional definitions. Then if you cut out the center, but only go out to 20, then it's really bad. You've learned nothing. But then you get to this magic white region, right? Where you take these rings far out that just tell you about the stellar halo. So this is sort of a guide for how to build some tracer for halo mass, right? Not the whole profile yet, but halo mass in this case. That, I don't think was really on people's radars before. So this is just one of the many things that we're trying to push on. So eventually all combine into one thing. So before we finish, I wanted to do one advertisement. So I heard some people here have used Colossus before, which is like a Python module for cosmology and so on. So I just wanted to say that there's now a Colossus web calculator, which you can just Google Colossus web calculator. An absolutely amazing undergrad in computer science at UMD basically coded this. I had no idea what was happening while he did this, but so it has basically the full functionality. So you can do complex things like multiple cosmologies, use CAMP to give me the power spectrum or something like that. And you can save all the data also and add them to your paper. Anyway, it's a fun thing. So just what I want you to take away from this talk is that with this orbiting infalling separation, even though it's really purely theoretical in a sense, I think we've learned a lot about what the halos really look like and why. And this new fitting function sort of hopefully captures this accurately once and for all. That's a dangerous statement, though. I'm sure someone else is going to do something better. Anyway, with these multi-wavelength sort of combined surveys, I think we really have a chance to use halos as these sort of laboratories where we can observe all kinds of fundamental physics. Thanks.
Thanks. Questions for the speaker?
Yes. Maybe it's a naive question, but in the beginning, when you showed the different files and the one traced by the satellite galaxies and the one traced by lensing, they were agreeing with some, that one there. You said that you thought that one is a coincidence that the two tracers are saying hitting the same result. Can you tell us why you think it's a coincidence and it?
Yeah, because so when you're measuring, I mean, the pink measurement you can sort of believe, right? I mean, the weak lensing tells you the total profile and, assuming everything's correct. Okay, fine, I believe it. This blue line is kind of crazy because, you're just counting satellite galaxies. So by the way, this is a stack of like 1,000 clusters or something like that. You're just doing the average satellite density. There's no reason to think it would be that simple, right? Because they live in, so subhalos are already not exactly a tracer of the dark matter, the full dark matter profile, at least not at small radii. And then the satellite galaxies occupy the subhalos in some really non-trivial way. And then your survey makes some cut in, I don't know, magnitude and color space probably, right? And then the profile somehow agrees, like it's too good to be true. And so Stephanie O'Neill, she's a student of Mark Vogelsberger's, she tested this in Illustris and it seemed impossible. I mean, it was crazy. I mean, she did all these different cuts basically on different satellite galaxies and you got totally different profiles. So I don't know. I think this is lucky to some extent, and I think the more we dig into this, the more this will turn out to be, yeah, just a coincidence. But that doesn't mean we shouldn't use satellite galaxies, right? Because they have, as you can see, they have higher signal to noise. But it's much harder to understand.
How do you know the model for baryons you alluded to towards the end is correct? Because that sounds like a risky territory in which the gas is still collisional, you have accretion shocks and stuff. So how easy it is to paint baryons to dark matter only simulation in that regime?
Yeah, so to be clear, right? So this is a super challenging, multi-year, extremely ambitious idea. When I get back, actually next week, we're hosting a hack week with all the people who are working on this, because we're like way behind. And we're like, it's all kind of crazy, and we're gonna just sit down for a week and try to hammer some of this out. So no, it's a good question, right? So the thing that saves us here is that very smart people, for example, Aurel Schneider and Roman have built already built models for the baryonic effects on the dark matter. Right, so there's a back reaction on the total density profile. And so in their model, what's really cool about it is you have a few free parameters, and they have shown that by changing those, you can reproduce all the hydro simulations, illustrious, eagle, Simba, owls, and so on, right? They just correspond to essentially different values of a few basic parameters, which are basically how far do you throw gas out of halos? Yeah, something like that, you know?
Is that territory something you can validate the observations yet, like SZ on that case, like?
Not really. So the best I can do for you, and this may not be good enough, is to say all of the different hydro simulations, including the extreme ones that people have thought to run, are covered by this parameter space, and then probably more, because you know you could imagine tuning the parameters further. Can I promise you that the real universe is in it? No. No, absolutely not.
But for example, this model by Roman and Aurel Schneider, you can validate using cosmic shear data on non-linear scales. So if you measure the cosmic shear on very small scales, so you see the baryonic effect, the separation to the nonlinear Battiferro spectrum, and then those recipes basically predict this depletion of the nonlinear spectrum.
Yeah,
all
that's
those
true.
things go around in this fashion.
Right, so you're talking about this plot where it's sort of the P baryonic over P dark matter only, right? Which has sort of a characteristic suppression on certain scales. That's true. So that is one plot that you can observe. I mean, you can do some observational tests. And the way it typically works out is that whatever you plot all these simulations on there, and then one of them looks better than the others, right? And it's sort of okay. And the model, since it can capture them all, at least can capture that. However, that does not necessarily, I mean, that's a sort of one-dimensional statistic, right? And so does that tell you the model is quote unquote correct? No, right? It just gives you some hint that it's not totally crazy. So I think this is the best we can hope for. And I think it's at least better to marginalize over all these parameters than to just sort of assume something. And it's also quite possible, I should say, that given the data, maybe we can't get any useful constraints on this. Right, that's completely possible. You marginalize over everything, and then your posteriors are basically uninformative, right? That can happen, and then you've learned that you just can't do it yet, and then you wait for better data, I guess.
Yes.
This serious discussion. You were showing the remarkable progress, by the way, but this is not my area. You were showing the phase space of the particles.
Yeah.
If I trust my eyes, I was seeing that the falling particles were like right below the orbiting particles. So in the phase space, they have basically lower velocity if I trust them. So does that mean that they're doomed to become orbiting particles at some point, and there is no way for them to escape?
Yeah, it's not a bad question at all, by the way. Yeah, basically, right? So I mean, so they have negative velocity here, that's hence infalling, right? And they will all turn into orbiting particles if they are bound, right? But bound is a really bad word in this field, in my opinion, because bound is extremely hard to define, right? So if you ask me, will these become orbiting particles? Yes, very quickly. They're quickly falling in, they would have a pericenter, and we will call them orbiting, right? If you ask me about a particle out here, it's not so clear, because that could be unbound, right? It could still be that it's going to make some sort of flyby move. And this actually, there is sort of there's one piece of dirty laundry here, which is really difficult, right? Which is, what do you call an orbit that goes like this? Is that orbiting or not, right? So you don't want to put a radius cut, but at some point it's like, well, if it never comes closer than I have 15 virial radii, like, I don't know, it's not really orbiting exactly, right? So this is difficult. So there's some sort of edge cases I'm still thinking about. Luckily, it's so few that it doesn't really change the profiles or anything.
They found that maybe there's something that implemented in the model, but all our the particles are blue. But I was just curious about that.
So the code is actually deliberately simplistic, you know, so it really just checks for the velocity switch. So you have negative velocity and you go to positive velocity, right? And it detects that basically, and then it does like very simple checks, you know, like that it's not spurious. So it's meant to be kind of simplistic.
This small satellite close to the center, no?
Yeah.
There's a small fraction of this satellite that is orbiting on the left, on the top left part, no?
This one.
Yeah, the other one of the.
Oh, this one.
Yeah, this one.
No, I
And
think
then
that's.
there is very infalling, the same satellite. And then the total basically a sum of two components.
So
You
it's
never thought
this
so.
thing, right?
Yeah.
Yeah, so no, it's nobody's ever picked up on this before. It's a good point. Yeah, so I think one thing that can happen, I mean, I haven't looked at this specifically, so the particles, they also orbit in the satellite, right? So the total orbit can be something like this. And that can be a little tricky to discern, like when does it become orbiting and falling, like when is the boundary reached. Again, it doesn't super matter for the output because then you just have a tiny difference in the time when it becomes orbiting. And that tends not to make a huge difference, luckily. But yeah, like these are tricky algorithmic things.
Yes. Nice to, by the way.
Thanks.
So what is, in your opinion, the best benefit of using the spread radius as alternative radius in which the mass function and prognosis distribution?
Yeah, I know it's been proposed. I mean, I think it's super interesting. I'm not sure it's really the best way forward for cosmology specifically. I mean, I'm interested in exploring it. The question to me is like, we have no idea really how to measure the splashback radii of individual halos, right? So to be clear though, right, we also have no way of directly measuring the virial masses or anything of halos, right? We're always using scaling relations. So the thing I feel like we would have to show, and I've been interested in doing this for a long time, I just haven't had time to do it, would be to see, for example, I mean, if I give you richness, right? So satellite number count, does it actually correlate more tightly with the virial mass or the splashback mass? And if the answer was splashback mass, you could then imagine building a richness-based proxy, right? And then trying to do some cosmology with that. But I think actually finding the radius of individual halos is impossible, right? So I don't really understand, I guess I don't understand the proposal there in a way. Yeah. So also I mean, I realized that I've contributed to this sort of splashback radius thing, but my take now, and I hope this came through in this talk, is that we should think about the whole profile, right? The profile contains information at all radii, and just focusing on the position of the splashback radius is sort of reductive, and also it's just a pretty difficult quantity to measure. So if you define it as the minimum in the slope profile, that's not always easy to measure in a noisy quantity, right? Whereas the whole density profile is, you know, I mean, it's something you can at least somehow constrain. And that really was my goal in proposing this new fitting function, by the way. The idea was that it should have parameters that sort of are non-degenerate and make sense and could ideally be constrained by observations. Does that answer your question?
So this fitting function will be complementary to an FW or file, or it is like an entire file that depends to all the parameters, the file, the mass, the concentration, and then additionally parameters. So the additional term, or it's a full profile.
Yeah, it's a full profile. So I mean, it really is an Einasto profile. Right? Full credit to Mr. Einasto. for this idea, though he didn't mean to apply this to dark matter halos, by the way. Anyway, and then yeah, you just multiply. I mean, it's an exponential sum, right? So it's multiplied by another e term, basically, that cuts it out. No, it's meant to be a full density profile. I mean, again, in my simulations, I really focus sort of on the larger radii. So if you want to ask like what is the density profile at very, very small scales, well, we still don't know that, right? Either in simulations or in observations, as strange as that statement may be. Right? I mean, there's these indications that you have cores, as in flat profiles, in these dwarf galaxies where people have looked. That's on pretty small scales. This is just such a vexing, hard question. My personal take is I'm not even sure it's a well-defined question anymore, right? Because maybe the baryonic effects are just so strong that you get quite big variations. You know, say you have some halo with a massive history of supernova feedback in a small halo, and it just totally has changed the dark matter profile. Maybe there is not one correct answer there. Does that make sense?
Any other question from home too? No, okay. Then we thank the speaker again.
So Benedikt is